not teach this last year because they have taken it out of the pre-cal curriculum. But as I am teaching my calculus class right now how to do limits, I have realized that you really need to know how to do this. So it is something that I'm going to throw back in here. They have not specifically stated it's in the curriculum. The curriculum's a little vague, so I guess you could maybe say that this still falls under rational functions. So it's not much of a stretch to put it in the curriculum. Also, it's one of those things like they're not testing it right now, so I don't know what they meant by some of it, but sometimes I would think it's not in the curriculum, and then I would see the test and be like, oh, there it is. Didn't teach that to you guys. So you guys will only have a teacher-made test, so that's no worry for you. All right, so advanced rational functions. What we're going to be talking about today are discontinuities. So discontinuities are very simple to explain. It's just you cannot trace the graph without picking up your pencil, right? At some point, you would have to pick up your pencil and move it to get to the rest of the graph. So the first type of discontinuity that we are going to look at are vertical asymptotes. So vertical asymptotes, the official definition that I'm going to give you is the y value goes to infinity or negative infinity, so it gets really, really big or really, really small as x approaches a given value. So you have a graph right here that has a vertical asymptote. We can see here, let me highlight it here. So, as you get closer and closer to that line, which is the place where x equals -2, if you're coming from the left side, as you get closer to that line, there go your y values down to negative infinity, right? Over here, if we approach from the right-hand side, as we get closer to that line, there go our y values up to positive infinity. So I think you guys are familiar with the vertical asymptote. I know we've seen them in the rational functions that we've just been doing here. So this is an example of a vertical asymptote that we'll see. It is one type of discontinuity that we will have, and I'm going to add this on here. Let me make sure I didn't put it in notes later. Oh, I did. Okay, so vertical asymptotes also are sometimes called non-removable discontinuities. So non-removable discontinuities includes other types of discontinuities, but a vertical asymptote is what we call non-removable. Discontinuity is removable if you can fix it by putting just one point there. Obviously, if we just try to put like just one point here, there's nowhere that you can fix the problem where you got to pick up your pencil as you trace it. You're going to have to pick up your pencil to trace it. So that's why it's called non-removable. So I'm just throwing that vocabulary out there in case you see a worksheet that may talk about that. I can't remember if I put it on today's or not. So what we need to know is what causes a vertical asymptote, because what we want to know is that just looking at the equation, where are the vertical asymptotes at, even without graphing, right? So, some of the more simple ones you can think of just by thinking of shifting the graph, up, down, left, right. So like if I look at 1 over x plus 7, that's a rational function. And Elijah, what has happened to that graph? What's that plus 7 do to the graph? Very good. So that vertical asymptote is usually at 0 right here. If we move it to the left 7, I'm going to have vertical asymptote at x equals -7. So some of these we could just think about, thinking about how we know we shift graphs up, down, left, and right. But do you guys know what number 2 is going to look like by looking at the equation here? No, we don't know that, right? We don't have a clue what that's going to look like. It's got squares, it's got x's in top and bottom, it's a mess, right? So, what we can do is anything that gives you a 0 in the denominator that is not canceled out is going to give you a vertical asymptote of the graph. So we could use that same rule here for number 1. So x plus 7, if you set that denominator equal to 0, and you solve that, you would just subtract 7 from both sides, and x equals -7. Right? So that's another way that we could do this problem. So for the second example here, that's what I'm going to have to do, because these will show up on a non-calculator section, right? So if I want to know what makes the bottom of this 0, how do I solve a quadratic like this without a calculator? You could do quadratic formula. That is a possibility, but if it's on non-calculator, it's probably not quadratic formula. Factor. All right, so I'm going to keep the numerator right here just because the next thing we're going to do, you're going to need it. And I'm going to factor that denominator. So, let's see, Zach Hawkins, if I factor that, I'll have an x here and an x here. What numbers do I need to use? -1 and -2. That'll give me the -3 in the middle. When I multiply them, I get the 2. That looks great. All right, so I want to know what makes the denominator 0. I don't care about the numerator. Right now, I don't care about it at all. In a minute, I'm going to show you why you do at least need to think about the numerator, but it doesn't matter on this problem. I'm just looking at the denominator. So now I would set each one equal to 0. You don't have to show this step right here, but I'm going to be extra clear about what's happening. So if we move this 1 over to the other side, x would equal 1. And if we move this 2 right here over to the other side, x would equal 2. So this would have vertical asymptotes at x equals 1 and x equals 2. And if I'm going to, one thing you can do when you're doing your homework, you can't do this on the quiz, but as you're working on your homework, if you want to confirm, just type your equation into Desmos. One thing I love about Desmos is it's so easy to type the equation in. It's so much easier than the calculator. And so this is the crazy graph that you get right here. If we type in those equations of our vertical asymptotes, we got x equals 1 and x equals 2. You can see those are our vertical asymptotes there. Our lines get closer and closer and closer to the graph there. Okay, questions on example 2? All right, let's talk about a point discontinuity. So a point discontinuity is when there is a hole in the graph, but the pieces of the graph match up. Sometimes it's called a point discontinuity. It is sometimes just called a hole. Call it a hole, that's fine. This is also called a removable discontinuity. So one thing that's really important for us to get better and better and better at is understanding how the equation matches the table, how that matches the graph, right? So one super simple way that we can graph something is to just plug numbers in, right? It's something that a lot of times students have even forgot they can do because it takes so long to do it. We don't usually do it that way. But I can just plug numbers in. So between negative 10 and positive 10, Bo, give me a number to plug in. Negative 6. So if I plug in negative 6, I've got negative 6 plus 5 over negative 6 plus 5. It's possessed. Which is negative 1 over negative 1. What does that give us? Positive 1. Okay. See, Matthew Bashir's give me another number to plug in. Something between negative 10 and 10. 3. Alright, so if I plug in 3, I got 3 plus 5. It does not like it when I write 5s. So that's 8 over 8. What does that equal? 1. So let me graph these points. I got negative 6, 1. I got 3, 1. Okay, Cade, give me another number to plug in. 8. So 8 plus 5 over 8 plus 5. You guys should be seeing a trend here. Hopefully you're noticing and getting aggravated that I'm even keep writing this out. I get 1. Alright, so 8, 1, that's right here. Okay, so it's looking like pretty much everything's 1. Right. Is there any number I could plug in that's not going to give me 1? Negative 5. Because if I plug in negative 5, I've got negative 5 plus 5 over negative 5 plus 5. And that gives me 0 over 0. And 0 over 0 is not 1. Any number divided by itself is 1 except for 0. Right? When you get to calculus, we'll learn a special name for this, and it's important that we know what happens. But right now, we're just going to call this undefined. And so, undefined, what that means is that negative everywhere on this graph, I'm going to get 1. Everywhere, except for at negative 5. So what I've got there is I've got a hole in the graph. And so if I graph it, it looks like this. It's just a horizontal line at y equals 1. Everywhere except for at negative 5. Now, if I graph this in Desmos, if I graph f of x equals x plus 5 over x plus 5, you can see there's my line. Do you guys see a hole anywhere? Okay. Desmos doesn't make it look like there's a hole there. If you graph it in your calculator, it's not going to look like there's a hole there. But if you can get there, it's hard to do sometimes. Oh, there it was. I lost it. Oh, you guys seeing it? Right there it is. So if you get right there at negative 5, it puts an open circle there. It puts a hole in the graph. So Desmos it's not going to look like it's a hole, and the reason for that is at negative 4.999999, it still equals 1, right? At 5.00001, those points really, really close to 5, it still equals 1. It's only if x equals negative 5 at that point. And remember, points don't even have width, right? You can get infinitely close to that point without ever actually getting there. So Desmos is going to graph it like it looks like a straight line. The way I have it here, it looks like, if you got 5.5, that looks like it's still in the hole, right? But the hole is actually just at that singular point right there at negative 5. So this is called a point discontinuity, obviously, because there's just a point on the line missing. It's also called removable, because if we wanted to fix this, we could fix it with one tiny point, and then it would be continuous everywhere, right? So that is why this is called a removable discontinuity. So what causes point discontinuities? What causes a hole in the graph? That is a 0 in the denominator. That cancels out. So, a lot of the problems you're going to see are going to look like this. It's going to say, find any discontinuities and describe each discontinuity. So, discontinuities only come from the denominator. So, whenever we are finding discontinuities, we want to look at the denominator. We only need the numerator for one thing, which I'm going to show you here in a second. So, what I'm thinking about is where that denominator equals 0, and to know that, I need to factor that denominator. So, if I'm factoring this, I'll have an x here and an x here. Let's see. Matthew Pelkey, what do we need to use to get that to there? Minus 3 plus 5. That'll give me the positive 2 in the middle, give me negative 15 if I multiply them together. That looks great. So now you will see that I've got an x minus 3 in the top and an x minus 3 in the bottom. And I can cancel those out. So, what this tells me is in my denominator, I have two places where x can equal 0. It could be x equals positive 3 or x equals negative 5. I'm only looking at that denominator to figure that out. These are both discontinuities. Okay, so both of these are discontinuities. But one is a hole and one is a vertical asymptote. Yes?
So even though they cancel out like x, you cancel out,
you still count it as a discontinuity. If they cancel, you're going to say this one right here is a hole in the graph or point discontinuity. But this one over here did not cancel, so that's going to be where we have that vertical asymptote. If you want to use a VA for that, that's fine. And if we look at this graph in Desmos, you can see at negative 5, I've got that vertical asymptote. But over here at 3, it looks solid, but if I can get there, I just saw it. There we go. If you can get right there at 3, you can see how it changes from a closed dot to that open circle. So it is undefined right there at 3. So that's what it looks like in the graph. So this looks like, it looks exactly like the graph of 1 over x plus 5 with a hole at x equals 3. So the stuff that cancels out is going to look like it's gone, but there is still a hole right there. Yes?
Will there always be something that cancels out?
No. So like on that last problem we did on example 2, nothing canceled, right? So I factored the denominator, but and I had a numerator there, but it did not cancel. So
it just means there's not a hole, but there's
two vertical asymptotes. Very good. So if it does not cancel, then it's a vertical asymptote. In this case, neither one of them canceled, so they were both vertical asymptotes in that case. So it is possible that neither cancel. It is also possible that both, like you have two and everything cancels and you only have holes. So it all depends on whether or not they cancel or not. So canceling is holes, not canceling is vertical asymptote. Miss White, who taught calculus before me, she used to sometimes complain that her students did not know their asymptote from a hole in the graph, which was fun. fun thing to say there. Slightly cool. Alright. So, for example 4, whenever we see these problems right here, we are going to factor, because we need to see what's going to give us zeros in the bottom and what is going to cancel, right? So in this numerator right here, I'll have my x and my x. Let's see, Lauren, how's that going to factor in the numerator? Perfect. X minus 3 and x minus 3. In the denominator, Sarita, how's that going to factor? Good. X plus 3 and x minus 3, because you need those terms to cancel out, so you got a 0 in the middle. That's great. Okay. Now, this is really important. We only look at the denominator for our discontinuities. Okay? So we got x equals negative 3 and x equals positive 3. Now, this x minus 3's we can cancel with one of the x minus 3's in the numerator, right? The other one stays there. So since the x minus 3 canceled, what do we have at this point? X equals 3 here as a whole in the graph. But over here, the x plus 3 did not cancel, so what do we have there? Vertical asymptote. It bothers students a lot of times that you got this up here that didn't cancel, and you didn't do anything with it, although technically it is at x equals 3. But the top does not matter, so it's okay. We don't even really think about that leftover stuff in the top. Right? It's just there. The only reason we even factored the top was just to see if anything would cancel. Okay, questions? Okay, so try these two on your own. Okay, so let's look at example 5. For this one, Paul, where do we have a discontinuity or discontinuities for this one? Good. And what type of discontinuity do we have there? Vertical asymptote there, because it does not cancel with the numerator. Be really careful also. There are children out there that try to do this right here. They try to do this kind of canceling, where they just like mark those X's out, and they've got 3 over negative 5, and then I don't know what they do with from there. You don't usually do it in this section as bad as you do it in some other sections that we see. Can I cancel like that? No, I cannot. Because I've got plus or minus signs in between the things that I'm canceling. In order for you to cancel, it's got to look here where in between the stuff where we're canceling, I'm multiplying right here. Those two things are multiplied. Here, this is multiplied. So you got to have multiplication in between them before you can cancel. You can't just cancel with plus or minus signs in between the stuff that you're canceling. All right, number 6 is a little tougher to factor that denominator. Somebody tell me what they got when they factored that denominator. 2x plus 1 and x minus 4. That one's tougher because you got to do the 2x and the x, and then you got to do a little guess and check there. But here you're getting negative 8x, positive 1x, which gives you negative 7x in the middle there. So that is factored correctly. So, for that one, let's see, Josie, where are we going to have discontinuities? Good. So we were doing x minus 4 is equal to 0, and that ends up being x equals 4. And is that going to be a whole or a vertical asymptote? Vertical asymptote. Good. All right, where else do we have a discontinuity? Okay, so 2x plus 1. One reason I wrote it out like this is because we just do this in our heads usually. But what you're doing is you're saying x minus 4 is equal to 0. So that's what you're going to do over here with the 2x plus 1. You're going to set that equal to 0. So how would you solve that for the x, Josie? Good. So you get 2x equals negative 1, and then divide by 2. So x equals negative 1/2. And is that one going to be a whole or vertical asymptote, Josie? That one's also vertical asymptote because nothing cancels on this one. Yes. Either one's fine on that one because it is one that rounds off. Like if you get 1/7 or 2/3 or something, I just stick with fraction because it's harder to do decimal for that. But now on Canvas, well, these problems are probably going to be multiple choice on Canvas. But if it ends up being a type-in box, it always has to be decimals pretty much on Canvas, so, or most of the time. So, but either one's fine. At this point, I expect you guys to know that they're the same. So whenever, the reason that we have, that's a good question. The reason that we have discontinuities here is because if I plug in a number and I get a 0 on the bottom of the fraction, that's undefined, right? Because if I'm trying to do, like if I plug in 4 into this equation, I would get 4 plus 4 over 2 times 4 squared minus 7 times 4 minus 4. And so that give me 8 on top. On the bottom, I got 16 times 2, 32, minus 28, minus 4. And you're going to end up getting 8 over 0. And 8 over 0 is undefined. Okay, so you get a 0 in the denominator. Right. Right. So what the numerator doesn't matter, right? So if I plugged in negative 4, because that's what would give me a 0 in the numerator, negative 4 plus 4 over 2 times negative 4 squared minus 7 times negative 4 minus 4, you're going to get 0. And on the bottom, you're going to get like, it's going to be 32 plus 28 minus 4, so it's 24, 32, 24 is going to give you 56, like 0 divided by 56 or something like that. What is 0 divided by any number? It's 0. That's a number. That's not undefined. Undefined is what gives us those discontinuities. And for undefined, the 0's got to be on the bottom. So the only reason we care about the top at all is to see if anything cancels, so we know it's a whole. So whatever's like this leftover stuff in the top, it bothers us. It feels like it should be an answer, but it's not because it's in the top and zeros in the top are fine. Okay, yes?
So you only cancel on the top when the top is on the bottom too, so
Correct.
with extra score you cancel out.
Yeah, so like we did not cancel these because this one was a plus and this one was a minus. But if,
Let's say it was X minus 1.
yes, we would cancel. We'd still have a discontinuity at 4, but it would be a whole instead of a vertical asymptote. Yeah, so whatever's on the bottom is always going to be a discontinuity, but if it cancels, it's a whole instead of a vertical
So
asymptote.
it is a big, you have something that nothing canceled in the beginning, you're going to have 2 of them.
Yes, unless it's like the first one where you didn't have to factor in the first place. Yeah. However, and you can actually have more than 2 in the bottom, but we don't know how to factor that, so I'm not going to give that. Well, I do give it to you, sort of like a bonus thing, but you'll see that whenever you get to it. But we don't know how to factor that, so if I do that, it'll already be factored out for you, which I don't usually do. Okay. So let's talk about something different. The way we answer these next questions is slightly different than the way that we answer the first ones. So the first ones we were just saying, here is our discontinuity. So I have put an super obvious statement up here as my first statement on this slide. If a function is not discontinuous, it is continuous. So that kind of is like, okay, thank you, Captain Obvious. This is, that would be an assumption everybody would make, right? So the reason I'm telling you that is because whenever you're going to get some questions that are, instead of asking for you to find the discontinuities, they want you to find where the function is continuous. So as long as you don't have a discontinuity, then the function's continuous. So it's going to say, like, is the function continuous on the given interval? So I've got 3x minus 7, and I want to know on this interval from -2 to 3. So what discontinuities would I have in 3x minus 7? What would give us a 0 in the denominator of that? Nothing, right? Because there is no denominator for there to be a 0 in. So if you're thinking about what you're looking at here, I think it's always helpful, especially as I'm explaining this, to look at Desmos. 3x minus 7, that's just a line. And I'm looking only from -2 to, what was that, 3. And so that's just like this piece of a line, right? It's continuous everywhere because it's just a line. So if you don't have a denominator, then it's continuous everywhere, and you're just going to say yes to this. It is continuous on that interval. If we look at number 8, Manuel, where does number 8 have a discontinuity? Not at 9, -9, because you would set this equal to 0, and you have to move it over to the other side, so you get -9 is your discontinuity here. So the question is this function continuous from 0 to 9? From 0 to 9, that's okay. Because it's -9 anywhere between 0 and 9. It is not. Now, if this had said from -10 to +10, then that would be a no because you have a discontinuity in that range. So because -9 is not between 0 and 9, this one would still be a yes. It's still continuous. so what you're looking at there, if you think of it on Desmos, is you got the function there. Let me zoom out a little bit so I can see it. There's its discontinuity right there at -9. But what you're doing is you're going over here and you're just saying 0 less than x less than 9. Oh, wrong thing there. And so all we're looking at is this portion of the graph right here. So my discontinuity isn't in that portion of the graph, right? It's just in this section, so this is continuous everywhere in that interval. Okay, questions? All right, let's see, CB, where is our discontinuity for number 9? Or how would we find it? Okay, so we're going to set that denominator equal to 0. What would we do from there? Okay, we're going to subtract that 2. So 3x equals -2. And then what would we do? Divide by that 3. So x equals -2/3. What type of discontinuity would I have there, CB? Okay, is it going to be a whole or a vertical asymptote? Okay, so to tell which one's which here, does 3x plus 2 cancel with the numerator here? It does, right? This cancels. So if they cancel, you're going to have a hole in the graph. If no canceling, that's when you have a vertical asymptote. So right here, we have a hole in the graph because those two factors canceled each other out. So we have a discontinuity. It's at -2/3. Is this function continuous from 0 to 1? Yes. Because once again, that doesn't fall between 0 and 1. I should have made one that was over, but I didn't. Okay, questions? Yes. It is -2/3. Yes. Yeah, on these, 3x plus 2 will not factor because you don't have to square there. So you're just going to set whatever you have on the bottom equal to 0. And so you'll have to subtract that 2, which is where you get that negative from. And then you're going to divide by the 3, which gives you that -2/3 there. And -2/3 does not fall between 0 and 1. If we had +2/3, it would be, and we'd say no for this. Okay, questions? All right, one other type of problem that we're going to look at. It's just worded just ever so slightly differently than the ones we've seen before. We're now, this time, instead of saying, is it continuous on this interval, we're supposed to tell where it is continuous. Give the intervals for which f of x is continuous. So for this problem, we need to factor top and bottom. So I'm going to give you a second, try to factor that top and bottom there. Actually, you don't even really have to factor the top on this one. Does it matter if it's a whole or vertical asymptote to answer this question? They didn't tell us we had to say anything about wholes or vertical asymptotes, right? So when you're telling where something's continuous, Like, it'd be nice to know whether it's a whole or vertical asymptote, but it doesn't matter because wholes and vertical asymptotes are both discontinuities. So, we're only looking at the bottom for discontinuities. We could just set that equal to 0 if we want. And if we do that, we got x squared equals 16. How do I get rid of the square? Square root both sides. And so I'd get x equals 4. But when I square root both sides, what do I have to put? Plus or minus. So plus or minus 4, I have discontinuities. Now, if you do it the other way, you'll have a little more information. So this will factor into x plus 4, x minus 4. You can see there's where you get your x equals negative 4 and x equals positive 4. So that's it. The top, let's see, how's that factor? Does it factor? Minus 4 here and a plus 3 here, I think. That'll give you a negative 8 and a positive 3. That'll give you the negative 5, yeah. So, this one right here is a whole because that term cancels. This one is a vertical asymptote, but it doesn't matter which one's which, so you could not factor the top if you wanted on that. So you have discontinuities at positive 4 and negative 4. So if you're thinking about your x-axis, here at negative 4, you've got a discontinuity. And over here at positive 4, you've got a discontinuity. I don't even have to know what the graph actually looks like. I know where those are at, right? So if you're giving the intervals where this is continuous, and we're using, it says intervals, we're going to use interval notation. Negative infinity is down here, positive infinity is up here. So we would go, always start furthest on the left. You go from negative infinity up to where's the first place we got to stop because we have a discontinuity. Negative 4. And did I tell you guys to use this symbol the other day? Okay. So this symbol right here means the union of the sets. It's kind of like saying, or this next set. So you'll see this used sometimes. I'm going to use it here. If you write or, it's fine also. And then, so I don't want to include negative 4, so I use that parentheses. So I'm going to start back at negative 4. And where do I go to before I hit another discontinuity? 4. And then, from 4, I can go all the way up to infinity without having another discontinuity. So you would write it like this. I don't like doing these because your answers are so long and a little bit annoying, but they're not terribly difficult. Okay, questions? Alright, let's look at that last one. Or not. Oh. Did I take that one off for you guys? Oh. I think I meant, let me make sure I didn't put any of those on the worksheet. No, I didn't. Okay. I meant to take 12 off, and I just forgot to take it off, so we're not going to do 12. I'm going to throw in some piecewise functions at the end of this unit, but we're not going to do them yet. So, we can ignore that for right now. So, for this one, do I have to factor the numerator? I don't have to because I only care about the denominator. That tells me where I have discontinuities, right? So if I factor that denominator, I could do x plus 3 and x plus 1. So I'll get x equals negative 3 and x equals negative 1. So if I'm thinking on that x-axis, negative 3 is down here, negative 1 is up here. That's where my problems are. Negative infinities over here, positive infinities over here. So I would go negative infinity to negative 3, negative 3 to negative 1, and then negative 1 to infinity. So you do not have to factor that numerator. But, just in case you run into this on a different type of problem, how do you factor that numerator, x to the 4th minus 81? X squared and x squared minus 9 and plus 9 there. Will it factor further? I can factor x squared minus 9. That'd be x plus 3, x minus 3. Can I factor this one? No, not with that plus sign. You can't do a difference of squares when you got that plus sign right there. So it's x squared plus 9. So this one right here would be a whole. This one would be a vertical asymptote, which it didn't ask for specifically, but in case this showed up on one where it did, that's what you would do. Okay, so you guys have a worksheet that's going to be your assignment for tonight. So go ahead and get started on this. On the back of the worksheet, you have two problems or you have a section that is called a challenge section. And so does anybody, there's the rules there, but if I have something like 8x to the 3rd plus 125, anybody know how to factor that? Every once in a while, Mr. Brown will show his class how to do this in Math 3. But I'm going to bet he didn't do this last year, considering we were already strapped for time. Coach Wood does not usually do this. But so the way that you factor it is you use that rule that I have on the back there. And so this is a challenge problem. So this is for those of you that finish early and need a little extra push because you are a math genius that is going to go do great mathematical things. And you need to stretch your mind a little bit. So this is how you do that type of problem. There's two problems down there below. So it's got an example. It's got the rule there. And so if you finish this worksheet, I want you to try to figure that out. And if you do figure those two problems out and have work, and could get up and show the whole class how to do it. I'm saying that because I don't want you photomathing all of this and hadn't tried it to see if photomath will work. But stupid photomath gives you the steps, so just asking to show you work doesn't even fix that anymore. But so if you can do that without photomath, then I will give you an extra point on the homework. So you can get a 5 out of 4 for that. So it's like making 125 on that homework assignment. So, but it is not required, nor shall it be tested except for possibly as like a bonus question on something. So do not stress out about it if you don't get the last two challenge problems there. Yes. Is non-removable. Yes. Yeah. Holes are removable, and vertical asymptotes are non-removable. It asks for both on this worksheet, and I do want you to put both, mostly because I want to get into your mind both of those terms, because especially in calculus, a lot of times you'll see removable or non-removable is the language they like to use. And I think on this worksheet I called it point discontinuity instead of a whole. Whole is a little bit informal, but I will accept it. There. And I haven't made the key to this, so I need to do that. If you have questions, you can come up here and ask me. Oh, I've made a crazy question, haven't I? Oh, vertical asymptotes, looking at number 4, especially those of you that work across, I'll answer this to everybody. So, I've made a crazy question here. I don't know if I meant to do that or not. Can't remember what I was thinking at the time. Okay, so for this one, you got, this is number 4, you've got x minus 2 over x minus 2 squared, which is going to be x minus 2 and x minus 2. And so you got an x equals 2 here and an x equals 2 here. One of these x equal to x minus 2's is going to cancel, making one of these a whole. And then this other one is a vertical asymptote. But you can't have a hole in a vertical asymptote at the same place. So, since these are the same, a vertical asymptote is always going to trump a hole. So, if there is a vertical asymptote, that is going to be your answer, because the hole sort of goes away because there's still a vertical asymptote there. So, if you find a hole and a vertical asymptote at the same point, you're going to call it a vertical asymptote.